Hello friends, I welcome you in lecture number 5 on complex integration. From last 4 lectures we are discussing about contour integrals, and in this lecture also we will discuss one more example on contour integrals. Before going for that example, we understand this remark. We can prove that if we multiply complex variable z with its conjugate, then we will obtain square of absolute value of z. We recall the definition of conjugate and absolute value of z. If z is x plus iy, then conjugate of z is given by x minus iy, that is replace I by minus I, and absolute value of z is given by square root of square of real part of z, that is square of x, plus square of imaginary part of z, that is square of y. And if we square on both sides, we will obtain x square plus y square equal to square of absolute value of z. So here this we can easily prove. Suppose we take z equal to x plus iy, and then if we multiply z with z bar, then here we have z equal to x plus iy and z bar is x minus iy, and we can apply that formula a plus b times a minus b equal to a square minus b square. We consider a equal to x and b equal to iy, and this is going to be x square minus I square y square, and we know that I square is minus 1 and there is 1 minus 1 in the product, so this is x square plus y square, and x square plus y square is equal to absolute value of z square. So whenever required, we will use this property that z times conjugate of z equal to square of modulus of z or absolute value of z. In other words, mod z square equal to z times z bar. One more thing, we have seen in earlier lectures also that if we have a circle with center 0 0 or origin and radius r, then we can write it in this form: z equal to r into e raised to I theta. Now if we consider z equal to x plus iy, then we know that absolute value of z is square root of x square plus y square, and if I take square on both sides, I will have square of mod z equal to x square plus y square. So this I can write in another form also. I can replace x square plus y square by mod z square, and that is equal to r square, and because mod z is always positive, we can write this in this form. If we take square root on both sides, we have absolute value of z equal to r. So this is another representation of the circle with center origin and radius r. Whenever we write absolute value of z equal to r, then this represents a circle with center 0 0 and radius r. If I write mod z equal to say 3, then this is the circle with center origin and radius 3, that is x square plus y square equal to 3 square, or x square plus y square equal to 9. So remember, this is the representation for a circle with center origin and radius r, and whenever required we will use it. We will always keep in mind that mod z equal to r represents a circle whose center is origin, that is z equal to 0, and radius is r. Whatever value here given, that is radius. So with this in mind, we try to solve this problem, or we find the value of integral of conjugate of z with respect to z along contour C, which is the right half of the circle mod z equal to 2 from z equal to minus 2i to z equal to 2i. And using this integral which we will obtain, Using this integral, we will find the value of integral of this function 1 by z along the same contour. So you can see here our contour is the right half of the circle mod z equal to 2, and now we know that mod z equal to 2 is circle whose center is origin. So it is the circle with center z equal to 0 and radius 2. Okay, this we can write that we know that mod z equal to 2 represents a circle with center 0 and radius 2, and we have to consider only right half of this circle between these 2 points, z equal to minus 2i and z equal to 2i. So first we roughly sketch this circle in the xy plane. Suppose these are the real and imaginary axis. This is imaginary axis or y-axis, this is real axis, and our circle is having center origin and radius 0 0. So suppose this much distance is 2 on y-axis, similarly this much distance is 2 on x-axis. Okay, we can roughly sketch the circle. So here we have a circle with center origin and radius 2. Okay, this is just for understanding. If you are comfortable without sketching the given contour, then also fine, you can do your integral without sketching the given contour, but this we just want to understand that what is the contour along which we are going to integrate. Now here center is origin, so here we have z equal to 0 and radius is 2, therefore this is 2, or we can write 2 comma 0. This point is 0 comma 2, here we will have minus 2 comma 0, and here we have 0 comma minus 2. If we want to write down in the notation of x plus iy, then here x is 0 and y is 2, so 0 plus 2i, that is 2i, and here 0 minus 2i, that is minus 2i, and we have to consider only right half of the circle between these 2 points, from z equal to minus 2i to z equal to 2i. We have to integrate along this part of the circle. This is the right half of the circle and this part is left half of the circle, and our contour is right half of the circle, which is mod z equal to 2. So this is our contour. This raided portion is the right half of the circle mod z equal to 2 from z equal to minus 2i to z equal to 2i. Now at this point, if we consider this point, suppose our point is at this point, then here theta is 0, and after traveling up to this point, angle will be pi by 2, and if we go in clockwise direction, in this downward direction, then here theta is going to be minus pi by 2. Because we want to evaluate contour integral, first we have to write our circle in the parametric form. So we know that if we have a circle whose center is 0 and radius is r, then parametric form is z equal to r into e raised to I theta. Here r is 2 and 2 times e raised to I theta, and because we are considering only right half of the circle, theta will be from minus pi by 2 to pi by 2. So here we will write minus pi by 2 less than or equal to theta less than or equal to pi by 2. So this is the representation of given contour along which we want to integrate. Now because z is function of theta only, we can find out derivative of z with respect to theta. dz by d theta is 2 times derivative of e raised to I theta is e raised to I theta into derivative of I theta with respect to theta is 2I, and therefore we can write dz equal to 2I e raised to I theta d theta. So we will replace dz by this expression in the given integral. Now we write a given function also. Given function is z bar. Z is 2 e raised to I theta. So we replace this by its conjugate. Conjugate of 2 is 2 itself, and conjugate of e raised to I theta is e raised to minus I theta. If we have two numbers in the product and if we are taking their conjugate, then this is equal to conjugate of z1 into conjugate of z2. Now 2 is real number, so conjugate of 2 is 2 itself, and conjugate of e raised to I theta is e raised to minus I theta. So our function is also converted in terms of theta. So now we can find out this integral of z bar along this contour C. So let me change the color here. So now I am writing integral of z bar. This is going to be z bar is 2 times e raised to minus I theta, and dz is 2I e raised to I theta d theta, 2I e raised to I theta d theta, and theta is from minus pi by 2 to pi by 2 along given contour. Now here this 2 into 2, 4, and I, that is independent of theta, so that we can take outside integral. And if we use the property of exponential function, here we have e raised to I theta into e raised to minus I theta, that is e raised to I theta minus I theta, that is e raised to 0, which is 1. So I directly write 1 here, and now integral of 1 with respect to theta is theta, and then we put theta equal to pi by 2 as upper limit. So pi by 2 minus lower limit is minus pi by 2, and this turns out to be pi by 2 plus pi by 2. Let me write one more step, and pi by 2 plus pi by 2 is pi, so we have 4 pi times I. So what we have obtained, therefore integral of this function z bar along contour C is 4 pi I. This is the first part of the problem. First we have to find the value of the integral z bar dz along this right half of the circle. Now using that obtained value, we have to find the value of integral of 1 by z along this same contour. So before going for that integral, we use that property. Now we know that z into z bar is mod z square, and we want to find out integral of 1 by z with respect to z. So from this, what I will obtain, now along this contour, along the contour C, our contour is mod z equal to C. So along this contour, absolute value of z is 2. So that we can substitute here. Therefore, along contour C, z into z bar is equal to square of 2, that is 4. So therefore z bar equal to 4 divided by z along given contour C, which is mod z equal to 2. Along the given circle, given right half of the circle, we know that circle is mod z equal to 2. So if we have any point on this circle, if we take any z on this circle, then absolute value of that z is 2. Therefore we can replace this mod z by 2 here. Therefore along any part of the given contour we can write z into z bar equal to 4, or we can replace z bar by 4 divided by z along the given contour mod z equal to 2. So this we can use in this equation. Along contour C we can replace z bar by 4 divided by z. So using this in equation number 1, or we can directly write that, therefore equation 1 becomes integral over C. Here we are replacing z bar by 4 divided by z, because along the contour we can replace z bar by 4 divided by z, and value is 4 pi I. So here we just replace z bar by 4 by z, and we keep other things as it is, 4 pi I. And therefore this 4 we can take outside the integral. Integral of 1 by z dz is 4 pi I. Therefore integral of 1 by z dz is 4 pi I divided by 4, and that becomes pi times I. Integral of 1 by z dz is pi into I. So using the first part, in which we obtain that integral of z bar is 4 pi I along the contour which is right half of the circle mod z equal to 2. Using this integral we are able to determine the value of this integral, and that is due to this property, z into z bar equal to mod z square. So sometimes they can ask you this type of problems, and here what is new thing, we have understood that if we have a circle with center, origin and radius r, then we can represent it in this form also. We have also used the property that z into z bar is mod z square, and we have seen that how we can use value of one integral to obtain the value of another integral. So this is very interesting problem, and we will continue with this type of problems in upcoming lectures. One more thing is, here we have written 1 by z, integral of 1 by z, and we have integrated along this circle, along the right half of the circle. So you can see our function, this 1 by z, is defined at every point on this right half of the circle. This function is undefined at z equal to 0 only, but you can see z equal to 0 is not on this circle, therefore this is valid. Similarly z bar is defined for all points in the complex plane, so there is no problem. So I stop here, and we will continue with this type of problems in this series. Thanks for watching.